I'm very pleased to introduce today's speaker, Bob Johnson from University of Virginia. Bob is a distinguished faculty member in the Department of Engineering, Physics, and Astronomy, I think, in his institution. That tells you about the scope of his research interests, which are incredible. And we're very lucky to have Bob visit us very often in CCPP, almost every fall by now. And once in a while, we ask him to update us what's going on in a very interesting subfield of physics, which has no coverage in our department. I would say in the department we are interested in stuff that's earthly or near earthly, and also stuff that's very, very far from us in astrophysics, cosmology, with some exclusions even in extra dimensions. However, we're lacking studies of solar system incredible objects, and the Cassini mission, which made some remarkable discoveries, is part of the story, which Bob is going to tell us about that, as well as the future missions, which we hope will have the same success.
Thank you. I walked down and there was a class finishing, and this was on the board and they were about to erase it. So I said, leave it. So if you get a little bored with up here, you can memorize this. Okay, so when Gregory asked me to give a colloquium, I talked a couple of times in the CCPP group about little particulars of things we do. I thought I'd give an overview of how some of our work at Virginia, and that I continue here at NYU, relates to some spacecraft missions. And I'm going to treat these in reverse order. The Europa Clipper, which is a proposed mission in 2024, would be the earliest. I bring this up only because last Friday were the dates for the instrument proposals to be due. So I've been working on this the last few weeks as part of a team that submitted 3 instrument proposals. We'll find out in April whether they're selected. And this is to the moon Europa, a moon of Jupiter. Then the next more recent one is going to arrive in July. It's been launched already. It's going to arrive in July at Pluto and go beyond there. And this September, if you've been following the New York Times and the papers, 2 spacecrafts, the MAVEN spacecraft from the United States and the MAVEN spacecraft, I love that name, from India, both arrived in orbit at Mars, and we'll talk about that briefly this September. And a thing that's been our bread and butter at Virginia for a while, in about 1994, we proposed an instrument for the Cassini spacecraft. The spacecraft was then launched in 1997. It took 7 years to get there, and it arrived in 2004. I gave a colloquium here in 2005 about it, and it's still going, and the mission will end in September 2017. All of you should be so lucky to get on such a program.
So when you say you go to, you mean you get to its gravitational field and you orbit around?
Yeah, not quite. These all orbit, this one will not. So we'll talk about, yeah.
It'll get close enough.
Yeah, well, we hope close enough. Yes.
Right.
So just to say a few words about the kind of physics we do. We've been interested, my background's in atomic and molecular physics, and so I got quite excited when I saw all these missions, and we've been applying this thing about to atoms and ions that precipitate into atmospheres and the short wavelength radiation to see what effect they have on atmospheres. And a particular process that's of interest to us is escape. That is, this radiation deposited in the upper atmosphere where the thermal conduction isn't great can put energy there and drive escape, and that plays a role in the evolution of these atmospheres. An example of that we worked on for years is Io. This is a telescopic image, amazingly, that just preceded the Voyager data. Someone asked me today in the student thing whether the telescopes were still useful for this, or were spacecraft more important, but this is a ground-based telescope image of the sodium gas that's being driven off Io, and you can look at it at any time and see this. So we are able to monitor an atmosphere on a small body that's escaping, and the escape is driven by the plasma impact. And this is an interesting feedback process because the plasma itself is formed from the escaping gas that gets ionized and picked up by the magnetic field. And so the type of physics we do is atomic collision and molecular collision physics. We develop cross sections, and then we put them into molecular kinetic simulations to try and describe the effect of the upper atmosphere with a particular focus on escape.
Where's that gas before it comes off?
Which one are you talking about? This?
The lower left.
Oh, that's in Io's atmosphere. Io has an atmosphere. Io's volcanic. The volcanoes release gases. Apparently the gases have some sodium in them in addition to sulfur. Sodium is only a trace species. Most of what comes off the planet is sulfur and oxygen and heavier species, but as every astronomer knows, sodium has a strong resonant line, and the first thing you see is sodium, even at an exoplanet, right? And then the other process I've been working on is, my training was in gases, atomic collisions, but when you're young and naive, you think that, okay, a condensed gas shouldn't be so different than a gas. Well, they're very different, right? Solid state properties and things like that. But lots of the moons and bodies we're interested in don't have thick atmospheres, so the plasma and the energetic photons reach the surface, and they modify that surface and drive things off the surface too to create a sort of ambient atmosphere. And this is the first moon of the Galilean moons of Jupiter, and that's what happens at Europa. Its primordial atmosphere is lost, and it has a frozen surface, and the plasma has access to the surface. And so that's the first thing I'm going to talk about. With that as a background. So why Europa? Well, if you remember images that you've seen, this is almost a true color image. You have to be careful with NASA. They like to highlight things and they change the colors, but that's close to the right color. Notice not many craters, almost none. It's an ice ball on the surface, but when the Galileo spacecraft flew by it a number of times, they noticed that the body disturbed the local magnetic field, so they were able to extract from that the induced field. It has no atmosphere, and the induced field is not due to the atmosphere. The conductivity they derived was such that it was likely an underground ocean. So we imagine the picture of an ice cap covering an underground ocean that's in contact with rock. And so this is considered an exciting target. That's suggested also by the following close-up picture of the surface, where you can see that that ice sheet cracks. It's the tidal heating, the stretching and compression of Europa that heats it in part, as well as radiogenic heating. And so when it does that, it cracks. And you can see in those cracks there are some other colors, right? And you can also see at certain places there, it looks like there might have been flow onto the surface, okay, with some contaminant that's not pure ice. Okay, and so the last suggestive thing that makes this an interesting body as a target is the fact that very recently Hubble Space Telescope images suggested that they saw Lyman alpha and oxygen coming off and at the southern pole, at the South Pole, and the scale of this is such that it wouldn't have been a small leak. It had to be something like a geyser throwing water molecules into space that became dissociated, and you see the Lyman alpha and the oxygen. This is actually pretty controversial. No one else has made the same interpretation, but being controversial is sometimes interesting, and it drives people to look harder for things like this. So here's an artist's image of what's going on. Europa has an ice cap. There may be warm ice that reaches the surface, causing those regions that have contaminants in. There are maybe plumes, if those measurements were right. it's bombarded by intense radiation. And that intense radiation, like I said in that second slide, can drive things into the gas phase. And so it's an interesting surface to consider.
So you have ocean, you have ice crust, and then you have something you call surface, but you don't.
Well, this has been modified. Okay, but I'll come back to that in a minute. It's been modified. There's penetrating radiation that changes the chemistry of that region. This is an artist's picture, okay? So you would like to send a lander there and drill down or something like that, but there's a little caveat. The intense radiation is such that it's about 540 rads per day, and 500 rads is considered fatal, I hear. Of course, we're not sending people there, so I guess we don't have to worry about fatal, but it means you need an incredible amount of shielding. And so prior to any kind of lander, a reconnaissance mission has been proposed. It's called the Europa Clipper. Why Clipper? Because it's going to be in a loopy orbit and only come by Europa occasionally. And so our question that we try to answer, based on our understanding of those processes I showed you first, is what can you learn about the ocean, maybe, from an orbit and not from landing and not going down and digging and measurement. So what we want to do is look at the composition, the morphology of the atmosphere, send instruments there that'll measure that, and then try and relate that composition and morphology to those surface features we saw. Hopefully, one will get some good information about what's in that material. Right now, it looks like salts, okay, and other things that might be from an underground ocean. And so, so that's the goal. And the instruments we're involved with were a neutral mass spectrometer, a UV imaging, and a millimeter wave imaging instrument, yeah?
What, the source of the radiation is the sun?
No, the source of the radiation is that plasma being driven off of Io that gets accelerated by magnetic processes, okay? And most of it is heavy ions of the order of 100 keV, very damaging, but a large fraction is also 10 to 100 MeV electrons that get accelerated.
So there's some like specific region where it's going to get bonked every time it goes by.
Yeah, it's a phase-locked moon, and so also a goal here is to find good sites to put a lander that may be protected. Okay, so what do we do? Try this just a little more in detail. We know something about, there's been a couple of missions there, we know something about the plasma that hits the surface, so we know something about the contents of the surface, and we can imagine what would happen if an ocean as we know it, material reached the surface. So we look at the radiation effects in the surface layer. These energetic particles maybe penetrate up to 1 meter, so the top meter is modified chemically. But what you would like to know is what's coming up here, if that's indeed happening. And so what we try to predict is what are we going to see in the atmosphere. This is just a schematic. What we're going to see in the atmosphere that might be connected with the various surface features. So we model the chemistry of the surface, and then we try and turn that into what kind of species you would see in the atmosphere. So that's the goal. It's pretty exciting. Ground-based measurements of sodium and potassium. Again, you can see these things from Earth with a telescope. Much more difficult at Europa than Io. But it looks like the ratios of sodium and potassium are such that they might come from models of an underground ocean. And so there's been some suggestion that this process of having an orbiter which goes by close to close to Europa occasionally, and then recovers and transmits back to Earth, and then goes around again, might be a way to do some reconnaissance. So, there's the Europa Clipper mission. Like I said, next July, the new Horizon mission will arrive at Pluto. As you asked, this is the one that's a flyby mission. I'll show you the trajectory in a minute. Pluto, we know, has been demoted because we now think it's not a planet in the usual sense of planet formation schemes, but has part of a group of bodies that's out in the Kuiper belt, but it has an atmosphere, a significant atmosphere, and it's mostly nitrogen and methane with a little bit of CO. And this is interesting because we want to know, this is presumably some of the debris left over from the formation of the solar system, so we want to know what is in this body. And so this mission is going there, the New Horizons mission. It was conceived and sent much more quickly than most NASA missions because it finally decided to do this when Pluto was already going on this way away from the sun. As you know, it goes into a large orbit, so the spacecraft has to chase Pluto. And so this was the fastest spacecraft ever launched. I don't know if you're interested in rockets, but it had it's an Atlas V with some 2 secondary levels here that once it got off principal and Earth gravity, it shot forward. But to give you a scale how fast it went, it was launched in January 2006 and got to Pluto in just over a year. The 2 new spacecraft that have just gone to Mars took 11 months. This took just a couple more months to get to Jupiter. So this was really a fast spacecraft. To Jupiter. Oh, 2,000 years to get to Jupiter. Now at Jupiter, it needed to get there for a gravitational assist. We don't have rockets strong enough to get all the way to Pluto. So it got to Jupiter really fast, got a gravitational assist, and the rest of the mission was a little slower, but it's out. It'll be arriving at Pluto next year. This is a list of instruments. I'm happy to talk about that sometime. And the goal is, after it makes this encounter with Pluto, because the spacecraft would have to have an enormous amount of weight to carry enough fuel to get an orbit around Pluto, and so it's just going to be a flyby. It's going to hopefully go out into the Kuiper belt and target one of the other objects that's farther out. So what's the mission like? Pluto is a binary system, and essentially it's got a large moon Charon that's about half the radius. Its orbital axis is such that it's tipped now and almost pointed towards the sun and the Earth, where it is. And so what's going to happen is the spacecraft is going to fly through the system. Now, before it was launched, we knew there was Charon. But then astronomers started focusing on the system, and now if you've been following any of this information, you know they've discovered 4 more objects. Well, that's pretty exciting. It makes it a much more complicated system, but there may be even smaller ones that they can't see, and so there's some concern that they will get through this system. The ones they see, they know the orbital parameters, they can miss those. It's the ones that they might not see they worry about. So
you have Nix and Hydra, is that what you're talking about?
Yeah, Nix, Hydra, and then there's 2 others.
That aren't on here.
That aren't on here, yeah. So anyway, so there's the encounter. It has a nice, reasonably modern set of, yeah?
Do you need to do GR simulations to get this precise in real life, or is that still like way too?
The people at JPL are incredible at guiding these space. Well, actually, this is APL. Sorry. And the engineers that do this are remarkable. They are able to adjust things, but they have to do it way in advance here because it takes 4 or 5 hours for the signal to get out to Pluto, so you can't make any last-minute maneuvers. So they have the orbital parameters. They tried to model whether there's other debris there and then drive the spacecraft. Yes, pretty accurately. I mean, okay. So anyway, the New Horizons is going to come through here, and the nice thing about this Pluto system being tipped on its axis, when it goes behind Pluto, and it not only gets close to them, but when it goes behind Pluto and Charon, it will have an occultation of the sun and an Earth occultation. Why is an Earth occultation interesting? Because it has the radio antennas that it sends messages back to Earth, and if there's an atmosphere, which we know there is, then that's deflected around the body. So it's going to have these occultations.
What's CA?
Oh, closest approach. Okay. So what about Pluto, and what about the Kuiper belt bodies? Pluto being one of them now in our classification. There's another one that actually the Voyager spacecraft flew close to some time ago. A moon of Neptune, that's a captured moon in a retrograde orbit that made close contact images of, and it has geysers. You can see the little plumes coming out. It has atmosphere similar to Pluto's. This is the kind of image we're able to get from Hubble Space Telescope of Pluto. So hopefully we'll have something like that for Pluto in the closest approach. But these atmospheres are such that they're all escaping. They're not escaping in this case because of the solar radiation, of the solar particle pressure that's on it. They're just escaping because the UV and EUV absorbed in the top of the atmosphere is sufficient to drive off some of the gas. Okay? And so we've been interested in modeling the atmosphere and trying to figure out how much gas is lost over time. And presumably that's happening on all these bodies. And so we're also doing modeling of that. But the encounter with Pluto will be in situ data that we can test what we're doing. Diagram of what Pluto and Charon, their size and what they might look like inside. And so when we model, this is a binary system. Astronomers are very interested in binary systems. This is a poor man's binary system. There is gas transfer between the major planet and the smaller body. And maybe just like there is between a binary star system, but much less robust. But anyway, we'll be able to test our models, and we predicted that Charon has no intrinsic atmosphere. But when the occultation takes place and New Horizons flies behind Charon, we predicted they'll see a nitrogen atmosphere that originated from Pluto and is frozen onto the surface and evaporated. So again, like I said, we're also studying the other Kuiper belt bodies. In those cases, we presume the composition may be similar, but they're different sizes and different distances from the sun. And so we try to relate those things to the visible properties that people see. It looks like the bright KBOs have retained all their nitrogen and the dark KBOs have lost their nitrogen atmosphere, etc. So,
sorry, what's causal? They're bright because they have it, or they lost it?
They're bright because at those low temperatures, the nitrogen will freeze on the surface and make a bright surface like an icy surface. Nitrogen would be the ice on the surface. You can't show a spacecraft thing without showing the launch, right? Maybe that's enough of a launch. Okay, so the MAVEN.
Power into space?
What'd you say?
Did the electric guitar power into space?
I still didn't hear that.
Sorry, I was just asking about the sound.
Okay. Oh, I see. Oh, I see. Okay. As I said, the two spacecraft went into orbit the third week in September. One of them, the MAVEN, that I showed the launch there, that some of my students attended. And the other one is the MAVEN spacecraft, Mars Orbital Mission. Very simple. This is a diagram of the MAVEN spacecraft. It's got solar panels, etc. And these are the instruments, if you're interested, we could talk about sometime. The path it took to get to Mars was similar for the two of them. And again, it's going to be in a loopy orbit where it goes down into the atmosphere, comes out, measures the solar fields, goes down into the atmosphere, measures the atmosphere, comes out. And both spacecraft will do something similar with different orbits. I couldn't resist showing the celebration at the headquarters, the space headquarters in India. I thought it had sort of a different take than we see NASA people. And one of my students who participates in this thing sent this and said it went viral in India. Okay. Cultural difference here. Anyway, the other interesting thing she pointed out that India is quite proud of this. It's the first Asian country to put a mission around the orbit of another body, and and the other thing is, they point out that it costs 10 rupees to take a rickshaw 1 kilometer in India, but it was only 7 rupees per kilometer to get to Mars. So this was a really low-cost mission, about 1/5 of the MAVEN mission. It has a smaller payload, but pretty impressive bit of work. Why Mars? Why is Mars interesting? Of course, you know a lot about it already. Ancient riverbeds, I'm sure you know. It was first noticed that when Martian meteorites, which were identified and picked up in Antarctica and places, were analyzed, they had carbonates, which suggested some water and processing of CO2 into the soil. And now we have rovers that have confirmed that actually, not just meteorites that have come here, but actually Mars' surface has some carbonates. The carbonates are a little hard to find, and it's debated, but they're there. And then the Mars Express, a European mission, has measured the ions that are being swept out of this atmosphere. And so where do the volatiles go? They can go into the crust, 2 places, right? An atmosphere into the crust or to space. Well, this is the process we're interested in modeling. And where does it stand? And what do I mean by that? Well, I had to borrow a little movie from one of our friends that's on the MAVEN team. It shows what happens when what their model of what happens when the atmosphere is exposed to the solar wind and things are dragged off. This is a little extreme, but anyway, gives you an idea that the plasma comes and constricts the atmosphere, yes?
So does it mean that Mars doesn't have a magnetic field?
Good, thank you. Mars doesn't have a magnetic field. It did have a magnetic field when it was formed. How do we know that? We know that because there are rocky areas that have crustal fields that have been identified, and so the fields were frozen into certain rocky areas, but the principal field is gone, and so now, unlike the Earth, it can be directly exposed to the solar wind. But the process I showed you is a little misleading because it's a nice, interesting feedback process like an IO. What really happens and what we model is you have an atmosphere that has some molecules at the top of it, not just atoms. And when it absorbs UV, it dissociates these species. The dissociated species then have extra energy, and the corona, we say, expands. So you have hot atoms making a bigger corona. Now the solar wind particles then interact with that and ionize those. And then the solar fields that are coming along with the solar wind drive those ions back into the atmosphere. These are now not protons and helium, which are light ions, but these are now carbon and oxygen, the heavier ions that are driven in at many keV energies into the atmosphere. And the impacting ions drive escape. This would be a model of one of our models at solar max under present conditions of what the escaping atmosphere might look like. These are all just schematics for here. I haven't put any numbers on, but that's the kind of modeling we're doing. This, there was an interesting coincidence, again, if you've been reading the papers, that occurred that Sunday, this Sunday, a comet flew close by Mars. It was unexpected. It was only learned about after both spacecraft were launched. And it came close enough, not that close, it's 130,000 kilometers away, but close enough that its tail and dust, the dust and gas in it, bombarded Mars at about 57 kilometers per second. That's pretty robust when you think of the solar wind, atoms and ions being driven to it. It's a comparable. And so this has been brushed by this comet, perturbing the atmosphere. To protect these spacecraft, they all hid on the other side for 4 hours or so. They changed their orbits so they were on the other side when the comet arrived. But now they've started already taking images of the comets. They had images just before this happened and images after. They're only now just being downloaded. And in fact, I was told by one of my students who works on this project that they put them down. They downloaded about 3 hours ago, so you could look on the MAVEN website. This is a Hubble Space Telescope image of this comet before it arrived. The comet is about, nucleus is only about 1/2 kilometer, but it was going to have a considerable perturbation of Mars' atmosphere. And here are 2 images from MAVEN. No numbers given. Okay, 2 images from MAVEN. They just loaded onto the website showing atomic carbon. And you can see how it's driven into space, and atomic oxygen in the UV, the 1304 line, and I forget what line of carbon this is, posted by my student. So what is our goals? We'd like to model to see if the water from Mars that was clearly there early in Mars history was lost to space or into the surface or some combination. So we'd like to constrain the space part. Right now it looks like there's a tentative yes based on what we've done so far. But now and based also on isotope data. But now we'll have this in situ data to model both the atmosphere as it's perturbed by a comet, and then after that's died down, the regular effect of the varying solar conditions on the upper atmosphere of the comet and how they drive escape. Okay, so that is exciting, and therefore I will finish by talking about our long-running work on Cassini. As I said, it was put into orbit in 2004. It's been there, it will have been there almost, here's where it is now. If you like a full season, it's tipped to the ecliptic. Amazing, we have a spacecraft that's been a full season at a distant planet like Saturn. It's the largest spacecraft that's ever been launched. It's going to be, it arrived in 2004, like I said, and it's already planned its final orbit in 2017. All but one of the instruments is still working. And of course, you probably know there was a probe that was launched from this spacecraft that went into the atmosphere in Titan and actually successfully landed on the surface and gave back information before it died. So there's an enormous amount of material here, but I'll just try to emphasize the kind of processes we're interested in. We think of this thing with its rings and tenuous rings and 62 moons and then this giant moon Titan, the second largest moon in the solar system. It was called Titan because they thought it was the largest moon in the solar system, but that's because it has this incredible haze and they weren't seeing the surface. Talk about that in a minute. But these bodies all exchange material between each other. They exchange material between each other because they live in Saturn's magnetic field. And so it's those processes, those plasma processes that drive stuff off the surfaces or out of the atmosphere and the rings and the moons, and then they're exchanged. And for instance, the oxygen seen in Saturn's atmosphere is not intrinsic to Saturn. It comes from the rings and the moons, and similarly with Titan. These moons are a zoo of different, we have sort of a picture of an icy moon there, a zoo of different shapes, a young surface like Europa with geysers for sure. The geysers were seen on Enceladus. An older surface, icy surface, Dione, heavily cratered. Hyperion, no one quite understands. It's like a sponge, obviously something that outgassed a lot of stuff. And then it turns out they made a close encounter with what also is a Kuiper belt object that was captured by Saturn. So this alone has been tremendously exciting to see all these different bodies close up with their reflectance spectra and composition being studied. But for something more fun came up recently. If you follow things on the web, there's a feature called the Pac-Man feature. I wasn't sure if everyone knew what Pac-Man was, but that was a little computer guy or gal, I guess, who ate things. Anyway, so this is showing a Pac-Man-like feature, but this is in temperature now. High temperature ice, in this case 96 degrees Kelvin, low temperature ice maybe down to 74 degrees Kelvin. Okay, but it's not the temperature that's interesting. Because it's in orbit and has different solar illuminations, you can also get the change in temperature. And what we found is the Pac-Man region has a low thermal inertia. And this region, which is not coincident with any geological feature on the surface, has a high thermal inertia. And by chance, we also notice that the energetic MEV electrons that are bombarding this moon, which is phase-locked to Saturn, have a pattern of bombardment just like that. So we think these energetic electrons are sintering this granular material, changing its thermal inertia. And so we're modeling that. A moon of Saturn, yeah. Yeah, thank you. Okay, so we have to finish with Titan, of course. Maybe one of the most fascinating moons in the solar system. Amazingly, the European contribution to Cassini was a probe, the Huygens probe, that actually successfully landed on the surface, which is a great story of how it was tracked and things. Riverbeds, ancient lake, pebbles on the beach that it landed on, pebbles coated though in hydrocarbons, okay? The hydrocarbon haze that made it look like it was a larger moon than we thought, and radar images of lakes. But none of this has to do with water, it's too cold. It all has to do with weathering by methane, liquid methane, clouds of methane, etc., also ethane. But from
The largest one is Ganymede, no?
what?
The largest moon in the solar system is
Ganymede is the largest, yeah. This is the second.
Jupiter.
It's a Jupiter.
Jupiter moon, yeah. The statement was that the largest moon turned out to be, when they realized they were seeing the haze, is Ganymede, Io, Europa, Ganymede at Jupiter, and this is the second largest moon.
Was it captured or is it actually?
No, this was formed with the Saturn system. Again, when we try to understand, I mean, there's so much of this that can be applied to exoplanets, because in this case, this moon is far from Saturn. The largest body is far from Saturn. At Jupiter, the larger bodies are close to Saturn. No one quite understands these different formation scenarios, which clearly involve some migration, which is the same as the case for exoplanets around their stars.
Isn't the picture from the landing thing that's coming from the beach?
This is from the lander.
And this is the only picture of the surface we have?
Well, this is a picture that they took on the way down. Oh, there's a whole potpourri of surface.
No, but I mean, it just landed and it's just...
It landed and it measured, it measured gas coming, because it hit the surface. It was an amazing engineering feat. It was launched from Cassini. Luckily, it didn't skip off the atmosphere. It actually went in. That was one of the worries. A large parachute came out, slowed it down. Too large, throw that parachute away. Another parachute came out, slowed it more down, throw that away, and a little tiny parachute came down, and finally thrusters, and it all worked.
And it remained alive after...
It remained alive for like an hour.
And only sent a few pictures of the surface or something.
Yeah, true picture of the surface.
No animals there.
I mean, oh no, no more coming, no more. I mean, these are radar images. Those are constant. Every time the Cassini spacecraft goes by, they take radar images of the surface, and those are turned, but these are sketches.
But this is an actual photo, right? It's light. No? Is it visible light? What is this?
Oh yeah, visible light. There's no, yeah, this is, and it's very dim visible light. That's why, because of this haze. Yeah, good question. I mean, we could talk all day about it. Okay, and so we're interested, of course, again, in the escape processes. Plasma and solar radiation come in. Something's driven off. We want to understand the isotope ratios. You understand that question because heavy isotopes escape less efficiently than lighter isotopes, so the isotope ratios differ from what they might have been primordial. And there's been a successful 108 passes through the upper part of this atmosphere. Okay? Now you'd think that since we had models based on the fact when Voyager flew by once, that with 108 passes we'd know everything. But as astronomers know, sometimes one bit of information is much more fun to deal with because you could make your model fit that. Whereas if you have 108 plots of the density versus altitude under different solar illumination conditions, different solar wind pressure, different things. But anyway, it's going to keep us in business for a while. But we do have nice things like this. Again, the Cassini spacecraft could see the atmosphere escaping. Here's a spacecraft approaching Titan. But those aren't photons that are being detected. Interesting enough, people are clever. There's a plasma, proton plasma, KeV plasma. When they pass through the escaping hydrogen, they charge exchange. When they charge exchange, they're no longer coupled to the field. They move in roughly a straight line if they're only going a short distance, and they come into your detector like a photon. So these are energetic hydrogen atom images of the escaping hydrogen. Of course, we want to model the full escape, but why is the hydrogen interesting? Well, if there's methane there and you dissociate it, the methane reacts and grows hydrocarbons, and it's the hydrocarbons that grow from the dissociated methane that cause the haze. Okay, but where is the hydrogen? There's no primordial hydrogen in this atmosphere. That was lost eventually. So the hydrogen we're losing, all those hydrogens have come from methane. So we have a model where we can look at the hydrogen escape and infer the methane precipitation rate, and therefore, clever chemists can then turn that into the growth of haze particles and things like that. Well, if you do this for a long period of time, and you have a reservoir of methane that we think we know there now because of the Huygens probe and the many passes through it, then you can see that the methane should all be gone. That's interesting. Should all be gone. So there must be a source. And of course, then people begin speculating if you have a source, if you need a source of methane, what could that be? Well, it's probably not a biological process. We've eliminated this one. Okay, but okay, so I'll stop there. And so this is an exciting time for planetary exploration, and we're thrilled to be a part of it. I've listed some of our short-term goals, my group at Virginia that's working on it, and my principal collaborators. And I find this particularly exciting now because of all the information that's coming down about exoplanets. This is going to be then ground truth, in a sense, for modeling those bodies, particularly when you see people already talking about habitable zones in exoplanet studies. Thank you.
You said that this comet, which flew by Mars, disturbed its atmosphere.
Yeah.
What if it passed Earth at the same distance? What we would see from
From the Earth?
Yes.
You might, well, mind you, there are telescopes that were being pointed at the whole time, and so I haven't seen what's happened. It was only Sunday. But you will see, you should see a brighter sky. We have a paper submitted that tries to describe how the atmosphere expands and how it should light up. And it's not been accepted yet. Maybe they will reject it after they get the results. We should have gotten it. But anyway, it might light up. You see it. But certainly from the spacecrafts, they're now, they came out from hiding. They have time to make an orbit and watch, and the perturbation should not have gone away, so the atmosphere still should be. So what you see is extra escape and expanded corona is what we're thinking, which then will help guide us to understand how this escape process really goes.
But it wouldn't be dangerous or something, right?
No, I mean the rovers on the surface had no problem. They just stayed put. In fact, they took images of the comet impact, and those are on the web too. They don't look so interesting. They're dots, okay, so the atmosphere is thick enough to, at the surface, nothing happens.
So following your last comment, in terms of exoplanets, the whole discussion about finding habitable exoplanets with an atmosphere would also imply that it's very important to understand how magnetic fields get generated in exoplanets.
Yeah,
And
well,
I see
okay.
you have
Yeah.
a project with their magnetic fields and escape from exoplanets, but in all the other talks I've heard about exoplanets, no one actually mentioned that.
No, well,
All the
yeah.
atmospheric modeling
Well,
that people want to do.
I have a brave new graduate student who jumped into this, Jake Turner, yeah, who jumped into this field. He's already done some observations because a few people have suggested they've seen the effect, magnetic field effects, the synchrotron radiation that would come from the interaction with the star, but he's shown that to be incorrect. But now he's raced around Europe this summer and organized an observing campaign to try and put some limits for a number of exoplanets on that. The magnetic fields clearly must play an important role, but we don't even know yet whether they have such fields. Does that answer your question?
So you mentioned that two probes entered the gravitational field of Mars in the 3rd week of September. One of them was from India, one of them was
Sorry, I'm not getting that. No, that's okay.
you mentioned that there were two probes that entered the gravitational field.
Oh, yeah.
of Mars, right?
Yeah.
In 3rd week of September.
Because of what?
In the 3rd week of September.
Yeah, they were both in September. They were only a few days apart. I think the MAVEN spacecraft arrived on the Sunday of the 3rd week in September, and the Wednesday, the Indian spacecraft. They had a little problem. They had a delay in their launch, but then they also lost their larger rocket. It wouldn't go, so they tried to beat the Americans there. They took a smaller rocket, got it into an Earth orbit, and then did a clever thing. There's something called the Ober effect, I think it is, where if you give little kicks at the right time in orbit, you can get the thing up. So they gradually kicked it 7 times and got into got into a heliocentric orbit and almost caught the American spacecraft.
More questions? Okay, if not, let's thank Bob for this wonderful